Hello everyone. Once again I welcome you all to MSP lecture series on interpretive spectroscopy. This is the fourth lecture in the series. In my previous lecture I started discussion on chemical shifts. The signals, we call it as chemical shifts. Let us go back to those few points. In NMR spectrum we get NMR signals. Okay, what these signals say about the molecule. So that means the number of signals shows how many different kinds of protons are present, and then the location of the signals shows how shielded or de-shielded. This is very, very important information. And then the intensity of the signals show the number of protons of that type. So one is different type of signals and where they are appearing, and then how many protons are there in each signal, and then the signal splitting. What is the splitting pattern, whether 2 lines are there, 3 lines are there, or 4 lines are there, 1 line is there. So this signal splitting shows the number of protons on adjacent atoms. That means how they are connected. As I mentioned, in case of ethanol, we have CH3, CH2, OH. When all these points will tell you where CH3 is located, where CH2 is located, where OH is located, and then how many different type of hydrogen atoms are there, and each one how many are there hydrogen atoms, and where they are appearing, and then the splitting would tell you whether CH3 is close to this one, something like this. So all this information again comes very nicely without compromising whatever the information we get from the bonding concept, okay, valence bond theory or molecular orbital theory. Whatever we get, exactly in the same way it proves the presence of these signals, these groups at appropriate place. So this is where the importance of NMR comes, okay, in characterizing molecules. So we call these signals as chemical shifts. They are measured in parts per million, and ratio of shift downfield from TMS to total spectrometer frequency in hertz will give you parts per million in ppm. And then as I mentioned, so this is when we measure chemical shifts in parts per million, this is independent of magnetic field strength. That means whether you measure chemical shifts at 60 megahertz, 100 megahertz, 300 megahertz, or 500 megahertz, or even in 1000 megahertz, the value remains same as far as denoted these chemical shifts in parts per million. So then we use the scale called delta scale. So for when we measure in parts per million, we use delta scale. And then just make you familiar with chemical shift terms, I am going back again to the basics what I discussed in my first lecture. So this one, induction of opposite magnetic field. So if you just see here, m equals plus half orientation of nucleus. Orientation of nucleus is like this, and then precision of electron density. So precision of electron density surrounding this proton, and induced magnetic field due to circulation of electron density opposing here, opposing the applied magnetic field strength. So that means applied magnetic field will cause the electron to precess about B naught, which in turn causes circulation of electron density and a generation of a small magnetic field Bi. You can see here, this is Bi here, in green one I have shown. So as per Lenz's law, the direction of an induced current is such as to oppose the cause producing it. So because of which it induced current, that would always oppose the root cause of that one. So hence direction of Bi is always opposed to the applied magnetic field. Now the net magnetic field experienced by the nucleus is B net equals B naught minus Bi. So the magnetic field experienced by the nucleus is less than the applied magnetic field, and hence a lower frequency. Now in order to cause transition, you have to apply a less frequency in a direction perpendicular to applied magnetic field. So whatever you are applying here. So that means the electron density surrounding the nucleus produces a shift to lower frequency. So as a result, what happens? you can compensate whatever the loss by reinforcing this one so that you can keep the Larmor frequency constant, or you have to bring down the magnetic field strength of the B1 that applied orthogonal to B0 that should correspond to now the precision frequency. So this is where the terms low frequency, high frequency, low field shift, up field shift, all those things comes into picture. So that means this can also be represented by B net magnetic field experienced by the nucleus, B naught into 1 minus sigma. Here sigma is referred to as the shielding constant. So if we keep the Larmor frequency constant, we need to increase the magnitude of B naught to achieve resonance, okay, as I said. So equivalent to whatever Bi is there, okay, whatever is there corresponding to that one you have to apply, so that B naught is strengthened now to neutralize whatever the effect of this one. It is called upfield or higher field shift. Okay, that's the reason it's called upfield or higher field strength, or also called diamagnetic shift. Why we are using term diamagnetic? Later we will be coming with another term called paramagnetic. Okay, so diamagnetic shielding and paramagnetic deshielding will come. So as a result of diamagnetic shift, all signals will be shifted to lower frequency. So whereas deshielding is referred to as downfield, lower field or paramagnetic shift, all shift to higher frequency, where the induced magnetic field will be reinforcing the applied magnetic field. In that case, what happens? Net magnetic field experienced by the nucleus will be much more than the magnitude of B naught. So that is called paramagnetic shift or paramagnetic deshielding shift. So the extent of magnetic shift is determined by the amount of electron density surrounding this nucleus. These points are very, very important. These 3 points I have shown here. The extent of diamagnetic shift is determined by the amount of electrons surrounding the nucleus, the ease with which electron density can circulate about B naught, and the magnitude of B naught. Okay, that means the amount of electrons surrounding the nucleus and also the ease with which electron density can circulate about B naught. That means how many electrons are there in the valence shell, whether they are spherically symmetrical or unsymmetrical field, and also the magnitude of B naught. At constant B naught, the shift is dependent only on the amount of electron density and the symmetry of the electron density. It's not only the magnitude of the electron density, the symmetry of the electron density is also very, very important in generating opposite field or applied field, in generating diamagnetic shielding or paramagnetic deshielding. Let us consider 13C nucleus here, I equals half. Here nucleus is surrounded by 1s2, 2s2 and 2p2 electrons. The valence shell in case of carbon we have 2s2 and 2p2. So 6 electrons are there. So that means here compared to 1H, the electron density is more and hence the magnitude of induced Bi will also be greater. So if you compare the nucleus of hydrogen kept in the magnetic field and 13C nucleus kept in a magnetic field, in both will be generating induced magnetic field. The magnitude of the induced magnetic field generated by carbon is much more than that of hydrogen, because their electron density is only 1s1, whereas here we have 2s2, 2p2. So now the electron density surrounding the hydrogen is spherically symmetric, whereas in case of 13C, electron density is due to 1s2, 2s2 is symmetric, but the same due to 2p2 is not spherically symmetric. So this is important. That means in case of 1H, still we have one electron is there, and then the 1s orbital is symmetrical, spherical. As a result, what happens? The electron density is spherically symmetric, whereas in case of 13C, so electron density due to 1s2 and 2s2 is spherically symmetric, whereas that of 2p2 is not spherically symmetric. So only way to obtain spherically symmetry is by having 1s2, 2s2 and 2p6, so that electron density is equal in all the 3 axes. If you imagine px, py, pz are orthogonal to each other, if all of them are completely filled, then you can have electron density equal in all the directions, x and y and z direction. As a result, probably there will be spherical symmetry. That means we are talking about a C4 minus ion. If not, with electronic configuration of 1s2, 2s2, 2p6, 2p2, it is not spherically symmetric, and it is very different from that of 1H. generated induced magnetic field. Here it is there, so I can write here, this is called whatever the reference is there, right side whatever it comes, low frequency shift, upfield shift, and then higher field, high field, and shielding. So here high frequency, because in this case what happens, it is reinforcing, so it is high frequency shift, and this is downfield shift, and high field is low field shift, and then shielding, deshielding. Okay. So this is how we designate with respect to reference here. So that means the lack of spherical symmetry for the electron density surrounding the 13C nucleus results in diminished circulation of electron density and hence lower BI. Okay. So that means if the spherical symmetry is not there, okay, the induced magnetic field would be having a small value. As a result, what happens? The shielding effect is minimum. I read again. The lack of spherical symmetry for the electron density surrounding the nucleus, 13C nucleus, results in diminished circulation of electron density and hence lower BI value. So thus shielding constant sigma can be divided into. So that means after considering the nature of the electron density, whether it is spherically symmetric or unsymmetric, the sigma, the term, can be divided into two components, sigma d diamagnetic shielding and sigma p paramagnetic deshielding. So this one can be divided into two. That means basically it is a combination of sigma d and sigma p, where sigma d is diamagnetic shielding and sigma p is paramagnetic deshielding. The sigma d results from the unhindered circulation of electron density, which produces Bi, opposes B naught, and hence is always positive. That results in shielding. So that means sigma d results from the unhindered circulation of electron density. Unhindered circulation of electron density happens when it is spherically symmetric, which produces Bi, and that always opposes B naught and it always positive. Then the net effect is shielding. Though sigma p results from the hindered circulation of electron density. When the electron density is unsymmetric, then that results in hindered circulation of electron density under the influence of magnetic field B naught, which produces Bi aligned with B naught or reinforces B naught. So in this case, what happens? In this case, if this is B, okay, B will be like this Bi, whereas in this case, this is applied. So in this case, this will also be like this Bi. So net is B naught plus Bi. So this is always negative. So that means the shielding constant is the sum of sigma d, total effect of sigma d and sigma p at a given time, whichever is dominating would decide whether the signal is shielded or deshielded. So now let us consider two examples of H2 and F2, ideal examples to look into these aspects, sigma d and sigma p components in total screening constant, shielding constant. So now if you just take diatomic species and apply magnetic field, you can have all possible orientations of these diatomic species, but you can consider the average of all possible orientations that falls into two categories. One is perpendicular to the applied magnetic field, one is parallel to the applied magnetic field. So that I have shown here. So this one, a diamagnetic molecule with orientation in perpendicular here, and then in this one parallel here with respect to the applied magnetic field. So here cylindrical symmetry relative to B naught is there. So that means the electron density around atom A is affected due to its bonding with another A. That means earlier when we had simple A, that's a different environment. Now we have AA bond is there, and AA bond has two electrons. Now the electron density around atom A is affected due to its bonding with another A, even hydrogen atom in H2 no longer has spherical symmetry because of the distortion of the electron density by the other nucleus. But in the parallel orientation of H2, the magnetic field, in this magnetic field, the electron density has cylindrical symmetry in the direction of B naught. Cylindrical symmetry is there in the direction of B naught. So this is not unimpeded and the paramagnetic component is 0. So here paramagnetic component is 0 in this case. But in the perpendicular orientation, the electron density around each hydrogen is not symmetrical with respect to B naught. However, so delta P is negative. So since hydrogen is only surrounded by 1s electrons and s orbitals are spherically symmetrical, as a result what happens? It is still the electron density is spherically symmetrical. As a result, the magnitude of sigma p component that generates because of hindered electron circulation that is negligible, and Bi only, and Bi is only 15%. So sigma p term for H2 is negligible. Though sigma p is so low and its contribution is about only 15%, as a result what happens? Sigma p term for H2 is negligible. That means it is only sigma d diamagnetic shielding what matters in case of H2 molecule. Now let us look into F2 here. For the F2 molecule, the analysis of parallel orientation and perpendicular orientations are very similar to that of H2. Each F atom has a closed shell of electron density. If you take F, so we have something like this. So something like this we have 88. So in this case, basically what happens in the perpendicular orientation, due to the presence of p electrons and the encumbrance of the circulation of electron density about B naught due to the FF field, bond produces paramagnetic shielding. So in this one, electron density is more, and also we are talking about p orbital. As a result, what happens? Circulation of electron density, there is encumbrance, hindrance is there. As a result, produces a considerable amount of paramagnetic deshielding. That means sigma p term is quite large. So actual shielding observed is average of the shielding in all possible orientations. If you ask me question, why I am considering only perpendicular, parallel and perpendicular? Yes, these two are taken after considering averages of shielding in all possible orientations. When you consider all possible orientations in all angles, you have to take two extremes. One is perpendicular, one is parallel. Only those two are considered. They are averaged one. So except for, because of this reason, except for 1H and alkaline earth metals, where we come across only s electrons in the valence shell, in all cases paramagnetic term dominates and hence deshielding is there. We should remember, if you consider 1H NMR, sodium NMR, or any other alkaline earth metal NMR, lithium NMR, in all these cases what happens? Paramagnetic term is not there and shielding is there. But apart from this one, if you go to any other metals, any other elements where we have p orbitals are there, p orbitals will be having valence electrons, the paramagnetic term dominates. So fluoride ions show a chemical shift of 400 ppm compared to bare fluorine nucleus, whereas in case of F2, the paramagnetic deshielding increases its chemical shift from 600 ppm relative to fluoride anion. So you can see the remarkable contribution coming from sigma p term because of hindered circulation of electron density as a result of p electrons. So this will give you some idea about paramagnetic deshielding and diamagnetic shielding, and also why we have, in case of 1H alkaline earth metals, a short chemical shift region, whereas in case of other nuclei we have a long range of chemical shifts. This is the delta scale. Chemical shift in ppm, I am telling you again, shift down from TMS in case of 1H and 13C, spectrometer frequency in megahertz. So here, as I said, if you measure chemical shifts in ppm, this is independent of magnetic field strength. So to compare that one, you can see here, I have taken 60 megahertz and 300 megahertz. And then if you take the chemical shift here, 1, 2, 3, 4, 5, whatever you have taken, it doesn't change. It doesn't change. It remains in ppm steady, whereas in hertz it is changing, but in ppm it doesn't change. So this is the advantage. For the same reason, always chemical shifts are given in parts per million, so that when you take in different magnetic field strength NMR spectrum, so it should not really matter. So now the location of signals. So after understanding this chemical shift, what is chemical shift and what is shielding, what is de-shielding, now let us look into the location of the signals. And the location of the signal is given by chemical shift. As I mentioned, if you just look into NMR signal, chemical shift of methane, it comes around 0.2 delta or 0.2 ppm. And then if you look into methyl chloride, it comes around 3. And then if you just compare between CH4 and CH3Cl, this delta coordination shift, the change in the coordination shift is 2.8. And then if you add one more chlorine, dichloromethane, if you take it is 5.3, again it is 2.3. And if you take chloroform, CHCl3, it is 7.2, and again difference is 1.3. That means addition of each chlorine atom, okay, changes the delta of remaining protons by 2 to 3 ppm. So that means it is additive here. You can see here, every time we are replacing one hydrogen by chlorine, the difference is increasing by about 2 to 3 ppm. That means it indicates nearly additive. So you should be able to check whether this holds good in case of all, or this is an exception. You can examine yourself. So that means more electronegative atoms de-shield more and give larger shift values. So that means here we have 3 chlorine atoms are there, and more shielding is there, more de-shielding is there because the electron density is pulled towards them, and so as a result chemical shift is larger. Okay. So then effect decreases with the distance. So here these chlorine atoms are 2 bond apart. Yes, if I write like this, okay, 2 bond apart, 1 and 2 bond apart. So effect decreases as the distance between these will move. So effect decreases as the electronegative atoms are moving farther from the nucleus we are considering. So additional electronegative atoms cause increase in chemical shift. If you keep on adding more and more electronegative atoms, so more and more de-shielding will be there, and then the chemical shift value will increase. So here I have given chemical shift values for different type of protons here. You can see here methyl groups in alkane comes around 0.9, and in alkane again if you look into CH2 groups it comes around 1.3, and CH will be coming at 1.4. And then if you have a CH3 group next to a carbonyl group, it comes around 2.1, and if it is next to acetylene, it comes around 2.5. Next, what happens if CH2 is next to halogen or oxygen, it will be in the range of 3 to 4, and next in the olefin, sudden jump is there, it is 5 to 6, and then when we have a methyl group in a olefin, it is again 1.7, and then if you consider OH group in phenol it is there, so it comes around 7.2, and then in this one CH will be red one I have shown here 2.3, and then in aldehyde it comes around 9 to 10, in acid it comes around 10 to 12, in alcohols it comes around 2 to 5, and then in aromatic alcohols it comes around 4 to 7, and of course here this is incorrect, so this is for this aromatic hydrogen atoms it comes around 7.2, whereas here for aromatic alcohol phenols H will come around 4 to 7, and amines it comes around 1.5 to 4, and sometimes it can also go much lower. I have given some nucleus again, and also I have shown their natural abundance and also the nuclear spin values and frequency with respect to hydrogen at 100 megahertz I have given, and also the standard references used while measuring NMR of various nuclei also I have given here. This again an important table. You can see 1H 100 megahertz. The standard we use is tetramethylsilane, we call TMS, and same thing is true in case of 13C also. TMS we are using, and frequency will be 1/4 25.1, and natural abundance is 1.1, and then 19F 100 natural abundance and frequency is 94. This is CFCl3 we are using as a standard. In case of 29 silicon again we are using TMS, and in case of phosphorus we use 85% phosphoric acid we are using, and in case of 77 selenium we use dimethyl selenium we are using. In case of 103 rhodium again 100% abundance, very interesting, and frequency is 3.2 times, and then rhodium metal itself is a standard there, and then 1117 natural abundance is 7.7 and frequency is 35.6, and then tetramethyl tin used as a standard. And again we have another one 1119, it's 8.6. In this case we use the same standard, and xenon is there, XeOF4 is the standard, and tungsten we are using Na2WO4 tungsten, and then in case of platinum we are using Na2PtCl6 sodium hexachloroplatinate, and in case of mercury we are using dimethyl mercury as a reference, and corresponding frequency with respect to 100 Hertz megahertz 1H NMR is given here. So let me stop here and come back with more interesting discussion on NMR spectroscopy. So have an excellent time reading. Thank you.